morning, everybody. Welcome back.
Lydia.
Hi, Lydia. Welcome back to Galois theory. Plan for today, we're going to start a new topic. We're going to talk about Euclidean domains. You know, get a little bit of Euclid mixed up in here.
Love that guy.
I've got usual office hours today from 1 to 2, tomorrow from 11 to 12, and 1 to 2. Don't forget, you all have homework set due Thursday, the first one of the semester.
It has not been forgotten.
Which I have definitely started.
I'm glad to hear it, Eleanor.
I actually have.
Good job. And if you try and start mine 45 minutes before it's due, you might be in for a fun time. Also, yesterday I posted homework 2, which will be mostly focused on like Euclidean domain stuff, as well as stuff that I thought might make Parker happy. And that'll be due next Thursday. Homework 2 only has 2 questions. So simple, so straightforward, so easy. You can totally start at 45 minutes before it's due and get away with that.
How many sub-questions does that have?
We know how to do number 1.
How many letters are in the questions? That's what we want to ask.
1 has an A and B, 2 has A, B, and C, I think.
Okay, that's like not terrible.
That's not the worst.
Okay.
I've seen
know,
G.
like,
Any questions or comments before we get started for today? Why do so many mathematicians, like me, Pete, Jonah, Seamus, Parker here, wear glasses? And Emily Rose.
Deceive with?
No, well, I mean, essentially it's to improve division.
That sounded like it hurt.
It's an appropriate one because today we're talking about the Euclidean algorithm. But just, Alright, so Euclidean domains. So we've talked about integral domains. We've talked about fields. Over the next few classes, we're going to look at all the lovely things that fall in between. So you may have already seen one of them, principal ideal domains, or PIDs. We're going to look at something today that falls in between fields and PIDs in a hierarchy of different types of rings. And that's going to be Euclidean domains, which are essentially rings in which you can do the Euclidean algorithm. So let's discuss. Oh, by the way, Lydia, you know where to find yours. By the way, since the last class, Lydia sent me an email saying that she appreciated all the comments directed towards her, and that when we said hi to her, she actually said hi back before realizing, oh wait, they can't hear me.
We can hear you, he's lying.
So, what's a Euclidean domain? Well, like I said, it's a domain in which you can do the Euclidean algorithm. So, I'm sure you've all seen the Euclidean algorithm in Math 410 at some point in your lives. Oh, hey, Andrew's not here. You've all seen Math in 410 at some point in your lives. Usually with regards to proving things with like cyclic groups and such. Back when we were proving like properties of cyclic groups, things like the order of any element in a cyclic group has to divide the order of the group. Pretty much all of those types of theorems end up using, proofs end up using the Euclidean algorithm, playing around with remainder terms and such. We'll do a little bit of a review of it today, but we're also going to talk about how do you generalize the Euclidean algorithm to rings that are not just working over the integers. So here's how you do. So I'm going to write down this definition first, and then we'll look at the standard example before moving on to something a little more exotic. So Euclidean domain is just going to be an integral domain, D. With a map delta going from your integral domain to the non-negative integers. So think natural numbers and also include 0 if you don't count 0 as a natural number. And you want it to set this map to satisfy the properties. There's 2 of them. First of all, delta of 0 is 0. Here, 0 refers to additive identity of your domain D. This 0 refers to 0, the number. And we also want to satisfy the property that for all elements A and B coming from your Euclidean domain D, with B not equal to 0, there exists, I should say there exists, not exists, Q and R elements in your domain such that A is equal to QB plus R, where delta of R is strictly less than delta of B. A equals QB plus R. That sounds an awful lot like long division, where you're taking A, you're dividing by B, you're getting a quotient of Q and a remainder term of R. So to start with, let's look at the standard example over the integers. So we need delta to be some map that maps integers to non-negative integers, so natural numbers including 0, in a way that makes it so that if you give me any two integers, A and B, we can write A equals QB plus R, with our R term somehow having a lesser delta value than our B value, the thing we're essentially dividing by. All right, Lincoln, how should we define a function delta that would make that happen?
F of little z equals absolute value of z.
I take issue with your F, because that is not an F, sir, that is a delta.
Oh, you're right, it is.
Yeah, our delta function is going to be take the absolute value. So let's do an example. Let's say A is equal to, I don't know, 11, and B is equal to 3. And you want to take A and divide it by B. Because essentially, when you're doing the Euclidean algorithm, that's what you're doing. You're doing division of your A by B. If I were to take 11 and divide it by 3, and yeah, we're doing it as long division. It's not very long here, but I don't want 11 thirds as the answer. I want a quotient and a remainder term. What would you say the quotient and remainder would be if we were to take 11, Seamus, and divide it by 3?
9 and 2.
3 goes into 11 9 times with a remainder of 2?
No, it goes in 3 times with a remainder of 2.
I was going to say, 3 times 9 is 27. I know everything about 27, sir. And you're not tricking me like that. Yeah, we're going to get a 3 remainder 2, right? Because 3 times 3 is 9, and then you have 2 left over that add up to give you 11. So here's the scoop. Here's our A, here's our B, here's our Q for quotient. Here's our R for remainder. Yes, Q can sometimes mean quotient in this class, Parker. So if we were to write this out
I'm not that insane.
in the form A equals QB plus R, what we did is our A value is 11, Q and B are both 3, our R value is 2, and we're essentially saying 11 is equal to 3 times 3 plus 2. A equals QB plus R. But wait, let's check Seamus's math even more. After me saying that there's a quotient of 9, I'm starting to suspect it a little bit.
He's sitting a little too close to Elmer. I think that's what's happening.
Sitting a little too close to last minute homework, girl? Okay. Does delta of B, or delta of R, our remainder term, turn out to be less than delta of B? Well, our R value is 2. What's delta of 2?
2.
Yeah, just absolute value of 2. which is 2. Delta of b, that's going to be absolute value of 3, which is 3. So is delta of r less than delta of b, Isabel?
Yes.
2 is in fact less than 3. So this checks out.
How did we get absolute value of n?
We asked Lincoln.
Yeah.
You just
So is it just any?
So usually when you do the Euclidean algorithm, you just let delta of n be n. The problem is we need delta to only, well, for proving things later on about Euclidean domains, we need delta to map to non-negative integers. And technically we could do this with like 11 over negative 3. We'd get like a quotient of what? 4 remainder 1 or something.
That sounds right.
Yeah. And we need to allow for the fact that these could be negative values
Okay.
that we're dividing by for A, B, and R, Q, and R. And so absolute value guarantees that our codomain is, our range is where we want it to be. That being non-negative integers.
So that's what that.
But we could have also had delta be n squared or something, right?
Could delta have been n squared? Then the Euclidean algorithm would actually work the same way, I'm pretty sure, so yeah. That would be, yeah. Which does give us interesting, just give us something interesting I was planning on talking about later. You have a habit of doing this, John. A single ring can have multiple Euclidean algorithms attached to it. In this case, technically that would be a different delta producing technically a different Euclidean algorithm. I say technically because then it all results in pretty much the exact same result, so it's not really functionally different, but it technically does behave a little bit differently. I place n squared with n to any even positive power, and you get something that works similarly. Yeah, don't remember your days of yore playing around with this?
Oh yeah.
Hutchinson crew, does this look like something you've seen once upon a time?
Yeah.
And you're one burnt. Wait, which? Never mind.
Haven't taken any classes from Murphy.
Alright, moving on.
Figure it out.
So, that's kind of the standard Euclidean algorithm, the one you're used to working with. Hey, you're probably used to thinking just delta of n equals n, and you didn't even think about the delta.
For sure.
Say what?
I just didn't agree.
Usually because when you first learn the Euclidean algorithm in, like, I don't know, high school or whatever, you've probably not worked doing it with negative numbers. Allowing for absolute value does allow us to talk about dealing with negative quotients and such. That's something to keep in mind. Let's get spicy. Let's do a new ring. We're gonna define a Euclidean algorithm on the ring of real polynomials.
It's just gonna be out.
Spicy.
Is this gonna be algebra 2?
The conversation.
Oh, polynomials?
Yeah.
I don't know. Maybe it is.
Yeah.
I don't remember what's in algebra 2, so I need to look at this for teaching classes.
Yeah, I do vaguely remember doing this.
So-
It was a while ago.
Let's say we had A equals x cubed plus 4x. B is going to be x squared plus 2. And I want to take A and divide by B.
Oh dear science.
Oh. How can I forget
I
about
forgot that this was a thing that existed in math.
I haven't.
To be fair, it's not something you do in most like college math classes.
So
I don't think I saw
this before you got to
That being said, it's going to be really useful in this class as we get into Galois proper.
Actually.
So, x cubed plus 4x divided by x squared plus 2. How do we do this long division?
That's an excellent question.
Isaac, I'll let you answer this because you asked about it earlier.
So the first thing we're gonna do, it still works kind of the same way, like you go by the pluses. So multiply the divisor by x so that when we subtract it, it'll cancel out the highest degree term.
Ah, because if we multiply x squared plus 2 by x, we'll get x cubed plus 2x. Okay, so we subtract that off, we get, these cancel, 4x minus 2x is 2x. So, alright, Isaac, what do we need to multiply x squared by in order to get 2x? And your answer better be a polynomial.
Well, let's call it a remainder.
Just call it a remainder. Why? Why you want to call this a remainder?
The degree is lower than you.
Oh, the degree is lower than x squared.
Yeah.
Yeah, so technically, this will be x, remainder 2x. Which is weird, because like a remainder looks bigger than the quotient, but that often happens with long division. Here's your q, here's your r. So, what exactly is our delta function then? The thing that says the remainder needs, if this is our b term, the thing that says that our r term is somehow smaller than our b term, or at least delta of r needs to be smaller than delta of b, in what way can we say that 2x is smaller than x squared plus 2? What property relating to polynomials specifically?
The degree of the maximum degree of the whole thing.
Just say the degree of the whole thing. Yeah. So here's our delta function. Delta is going to take in real polynomials and it's going to spit out non-negative integers. I'm just going to say z plus and keep in mind that that is going to include 0 because I don't want to keep writing out natural numbers union set containing 0 each time.
You could just write n.
I could just write n, but I'm so used to n thinking of it starting with 1.
No, that's nx. And
There's so many different notations out there, Isaac, okay? The one I'm used to in like every math class I've taught is n means start at 1.
I am
you
also
haven't had
used to
enough
that way.
computer scientists around here.
Well, yeah, I know computer science, you typically.
Just
Dr.
call it
Look,
the cipher.
both ways have both ways cause their own issues in various
That's right,
points.
the cipher set.
Just have
Also,
Half an after number starts with 2.
Dr. Gabler likes to what?
I said 0 as well.
Good for Dr. Gabler.
He's more than you.
What?
Uh-oh.
I'm a computer scientist. I have to fight about this. It's a
No.
requirement.
No, you don't.
No, you don't.
You really
You have
should
no
give up
power
on
here.
this.
I'm shutting down.
No, I was talking to Isaac. Isaac.
Okay, this is what I was worried about. So what's going on here? So what we actually showed here is that if we try and write out our A equals QB plus R equation, our A is x cubed plus 4x, our B term was x squared plus 2. We needed to find a Q and an R that are in the set. That's why I said your quotient remainder better be polynomials, is because they need to be in the actual ring that we're looking at. Wowzers. Our Q, we found, was just x. And our remainder term that we found was 2x. And this gets the job done. It satisfies that delta of b, which was equal to the degree of, since our b, x squared plus 2, which is 2, turns out to be greater than delta of r, which was degree of just plain old vanilla 2x, which is 1. As a reminder, degree of a polynomial just means take the highest power of x that you see showing up in that polynomial. And that gives us another Euclidean algorithm that works on real polynomials. What's that?
Wild.
Quite. Questions, comments, concerns? So in other words, you can sort of think about it as a Euclidean domain is like, it's like a domain, ring, where you can do long division. Everybody's favorite thing to do in math class.
Seems like it would be a lot harder to do that over
Actually, in this class it probably is. Sorry, one more time, Elias?
Seems like it would be a lot harder to do this over the integers, so integer polynomials.
Oh, okay, let's talk about this over the integer polynomials. Can we do this? works out over the integer polynomials.
What if A was 3x cubed plus 4x and B was 2x squared plus 2?
Alrighty. Okay, all about that. What if? Well, in this case, we'd have our A would be 3x cubed plus 4x. Our B would be 2x squared plus 2. We need to find some q to multiply it by, and some remainder term. Where the degree of R would have to be less than the degree of B, which is 2. So R can be a linear polynomial only,
Oh, strictly.
strictly less than. So here's the problem. What do we need to multiply B by in order to make this happen?
3 halves x.
Well, to get from 2x squared to 3x cubed, there's no way about it. We would have to have a 3 halves x in there, plus something times something. No, we can't make up for it in the remainder term, because the remainder term can't have an x cubed in there, because otherwise its degree would be too big for the remainder condition we have. So, okay, why don't we just have a 3 halves x in there? Matthew?
That's not of the rules of integers, right?
3 halves is not of the rules of integers. That is a fancy way of saying it's not an integer, but yes.
Could you, like, in theory, multiply both sides by 2, though? Like, if you take
Multiply
a...
both sides by 2. Okay. 6x cubed plus 8x, 4x squared plus 4. Same issue.
Right, no, but now, okay. Oh, yeah, I guess you're saying. Yeah.
I get what you're getting at, but then you would need a new. If you multiply both sides by 2, you would get a different q term that you would need, and it would be what, 6/4 instead of 3 halves, which
Right.
you know 6/4 might look better to you than 3 halves, but I assure you it's not. Now the problem is, this doesn't work. Unfortunately, because you could do it over the real polynomials. You could have this work over rational polynomials if you wanted to. You can't get it to work over integer polynomials. Why? Because you end up with having to multiply by things that are outside your set in certain circumstances.
Is it possible to get a different delta so that more things would go with the remainder instead?
Good question. When we say, does this work over z of x, just because this Euclidean algorithm doesn't work doesn't necessarily mean there couldn't be some other Euclidean algorithm. The long answer to your question is no. There is no delta that will get the job done, as we will prove. As we will prove because we're going to prove that every Euclidean domain is a PID. We know that z of x is not a PID, or at least you know that from stuff last semester, therefore it cannot possibly be a Euclidean domain. That's the long answer. Well, not the longest, but the long answer. We'll talk about the longest answer in due course. So, unfortunately, our good old friendly Euclidean algorithm for long polynomials works over a real polynomial long division, but we can't necessarily just do integer polynomial long division because we could end up with quotients, for instance, that end up not lying inside of the set. Questions, comments, concerns? Lydia, any questions from you?
That was a great question.
Oh, Parker liked your question. I didn't like it as much, so I'm not going to answer it. So, what can we say about Euclidean domains? Well, the first thing we can do is it's actually a fairly short proof to prove every field is necessarily going to be a Euclidean domain.
But not necessarily accurate.
Oh, I don't know. Does every Euclidean domain have to be a field?
I don't know.
I think you have enough information to answer that question.
I don't remember what PIDs are fields or not.
Not all PIDs are fields.
There you go.
Can we think of, based on what we know so far, can we think of anybody think of a Euclidean domain that is not a field? I know we only have 2 Euclidean domains so far to look at.
The integers?
The integers.
So proof.
Also real polynomials. Integral domain that doesn't form a field because you can't divide by x.
Right.
So technically, every example of a Euclidean domain we've seen so far is not a field.
By induction.
By induction, we conclude none of them are. Well, then this theorem is about to prove there does not exist a field, so that's so that is a sad thing.
Galois theory over.
Actually, yeah, that would end this course very early on.
All things inconsistent, go.
Extra hour.
I'm gonna write ED. ED is short for Euclidean domain. You'll see me write this a lot throughout the semester. Get used to it. It's like PI. I'm gonna write PID when I mean principal ideal domain. Get used to it. So here's our proof.
His name is Ed.
What's that?
We have a new member of the class. His name is Ed.
Ed. Oh yeah. Hey Ed. Hey Ed. Did you know that every field belongs to you in the world? In the universe, even it's true.
Man,
So all right, let's let KB think. And what we're going to have to do is we need to find a way to define a delta function. We already know, by the way, all fields are integral domains. I'm not going to go over proof of that again, but that is a 410 result, and if you haven't seen it yet, just believe me for now. Be happy to prove it for you in office hours. So we're going to let K be a field. So K is necessarily an integral domain, and we need to define a delta map that'll get this job done. And we don't know anything about K other than the fact that it's a field. Meaning all non-zero elements, i.e. all elements that B could possibly be, are going to have inverses. Turns out if every non-zero element has a multiplicative inverse, there's a lot of deltas you can choose.
You just have, well, we know that delta of 0 is 0. So,
However we define delta, that needs to happen.
if you had delta r, if you had r be 0, then delta r would be 0. And 0 is almost certainly less than delta of b.
Well, depends on what delta of B is. Could be equal to.
Yeah. Does it have to be?
Nothing in our
It has to be
condition.
strictly less than.
It has to be strictly less than.
It's at least a starting point.
So we're going to define function delta from K to the non-negative integers. Does anybody have a favorite positive integer? Matthew, what's your favorite positive integer?
24.
24. It's a good one. I'm going to prove. Let's say delta of A. We're going to map everything to 24 as long as A is non-zero.
Well, that's easy.
That is a function that satisfies delta of 0 is 0, and that takes in every element in our field and spits out a non-negative integer. As a side note, there is no reason why delta needs to be something like continuous or differentiable. I will throw out. This needs to satisfy these 2 bullet points.
We've already had one that isn't middle well.
Oh, that's
Absolute
continuous.
value is not
It's like
technically
opposite.
differentiable.
Technically, that is a differentiable function over the integers. Because every integer is an isolated point, so every function of the integer is technically differentiable everywhere. Think vacuously true type reasons.
It's dense with nothing.
So now we need to check that given any A and B in our field, we can find some Q and R that gets the job done. So given any A and B coming from our field, we need A, that's our A, is equal to some Q times B, that's our B, plus something that'll be our R term. How can we do this if we're working over a field? I should also note B not equal to 0.
I patched my idea. So it can't, well yeah, B can't be 0 because if
Well, then R would have to be A, and that is not guaranteed to have delta of R less than that.
yeah, you have no, yeah, so then you already wrote it B, so yeah, make quotient, okay, why did you already write it? You guys work on it.
Wouldn't you just make it Q equal A times inverse B?
Okay, what would this be?
0.
Yeah, we're working over a field, so if B is non-zero, it has to have a multiplicative inverse by definition of field. So just take A over B, which yes, you could write as A times the multiplicative inverse of B if you
Now,
prefer.
that's what I wanted to see.
Okay, well now you can see it. Where delta of R, which is 0, is going to be less than delta of B, which since B is non-zero, what is delta of B?
24.
24. Boom! There's our proof. Every field is an every field is an integral domain, but every field is a Euclidean domain.
Because you can divide stuff.
Yeah. As you can see, there's a lot of ways of defining Euclidean algorithms because in a field you can always make R equal to 0 no matter what. So you just need non-zero terms mapped to non-zero to strictly positive integers, and any delta will get the job done in that case.
So is R always going to be 0 in this Euclidean?
It doesn't necessarily have to be for defining a Euclidean algorithm over a field, but you can define a delta in such a way that will, which makes it a Euclidean domain.
Okay. So if you had like A plus 1 times B inverse,
A plus 1 times B inverse,
that
and then have a R be what, -1?
Yeah.
Well, then you might run into a problem in that, okay, delta of -1 would be 24,
Exactly.
which would not be less than your delta of B.
Yes.
So that specific specific delta, or that specific way of doing the Euclidean algorithm would work. But in order to have a Euclidean domain, you just need to have one way of finding a Q and an R for every pair A and B. It doesn't have to be every pair Q and R works. You just need, given an A and a B, can you produce a Q and an R that will get the job done? In this case, yes, here is one way of doing so.
Okay.
There are many ways of not doing so, but
Okay.
we don't care about that. Any other questions or comments about this theorem? So, every field is a Euclidean domain. Turns out every Euclidean domain is going to be something else that is spicy called a principal ideal domain, or a PID. Emily Rose, do you remember what a PID is from last semester? She had to look at her notes. No.
I wouldn't even be able to say yes either way because regardless of whether I remembered, I already looked through the packet.
Oh, wait. Okay. PID, principal integral domain. Doesn't that mean that
Ideal.
principal ideal domain? Doesn't that mean every single sub? I know that
Every ideal.
Every ideal is a principal ideal. Is what I remember.
That is true.
Yeah.
What does it mean for an ideal to be principal?
It's principal if that's the smallest way you can write it. I think if that thinking about it correctly.
It's an ideal where it's a ring where every ideal can be generated by a single element,
Like the integers.
like the integers, for instance. So, those of you who haven't seen this, a principal ideal domain last time you're going to see me write that on the board, it's going to be PID from here on out, is an integral domain where every ideal can be generated by a single element. Meaning, if S, big S, is an ideal in PID R, then we necessarily know that there's going to be some element, call it little s, I don't like little s. Call it little t. Fine, I added little s in the packet. I'll be consistent. And for some little s in big S is going to be equal to the ideal generated by little s. What is the ideal generated by little s? Well, by definition, it's just going to be the set of all multiples of little s coming from your ring. So in other words, a principal ideal is one where every element in your ideal is some multiple of the same element in the ring. Some multiple of little s in this case. And in PID, every ideal can be written like that. So let's take a look-see. How about the integers? Are the integers of PID? Well, what do all the ideals look like in the ring of integers? For that matter, what do all the subrings look like in the integers?
They look like NZ.
Yeah, just multiples of some n. Any ideal in Z has the form NZ, which is the same as ideal generated by n. 2z, 3z, 4z, 5z, 6z, negative 20z if you're feeling frisky. So, what does that tell us? Integers form a PID. Yes, Matthew, these triangular brackets do not mean the same thing as, strictly speaking, as cyclic group generated by n. In this case, they actually do, but in general, they do not. Usually, I'll try to make it clear. And if it's not clear what I mean by these triangular brackets, blame some French mathematician. Not Galois, but I forget who exactly standardized that notation. How about this one? Real polynomials. You can have things in here like ideal generated by 2, which is any real polynomial that is a multiple of 2. Instead of all 2 times f of x, where f of x is just some real polynomial. You could take ideal generated by x, which is going to be a set of all polynomials that form x times f of x, where f of x is in R. You've seen this ideal before, ideal generated by x in real polynomial land. What is that equivalent to, saying that something is a multiple of x?
It means that the constant term is 0.
Yeah, in other words, the constant term is 0. Or if you were to plug in 0 for x, you would get 0 as your output. So we could say the set of all g of x such that g of 0 equals 0 would be another way of describing that. What do you think? PID, yay or nay? A vote for yes, 2 votes for no. Rose, why not?
Because the whole set is an ideal and it can't be generated with only one element, it needs 2.
I beg to differ. Would you agree that every real polynomial is equal to some real polynomial times 1?
Yeah.
Well, then, that's how you can generate the whole thing. So I don't like your argument. Isaac?
Well, if you have something like x plus 2.
Oh, x plus 2. You could do that. Ideal general set of all polynomials that are multiples of x plus 2.
No, yeah, I was thinking it didn't fit into any ideal generated like that, but then there's one.
I mean, you could just say the ideal generated by x plus 2.
It's also per x.
That's principal ideal.
Yeah.
Oh,
Seamus?
I mean, any just constant ideal of this is equal to the whole thing, which is something we've put before. Yeah,
As long as it's not 0.
okay, yeah.
Yeah. Result you may or may not remember about ideals. If your ideal contains a unit, meaning if there's any element in your ideal that has a multiplicative inverse, it necessarily is going to have to be the entire ring.
Yeah.
So since all non-zero constants are units in here, any non-zero constant n is going to generate the whole thing. Parker?
I do remember that if we did something like the ideal generated by 2 comma x, in the reals, I'm pretty sure that's just equal to the whole set.
Because 2 is a unit. So that's principal ideal. You can generate it by 2 or 1 or 5 billion.8 pi squared.
Time goes
No, well, don't get I mixed in, because then it's not real anymore. So none of you have given me any non-principal ideals yet.
what if we had like generated by x and x plus 2?
X and x plus 2?
That's just equal to.
Well, then, since the ideal has to be closed under subtraction, it's going to contain x plus 2 minus x, which means it contains 2, which means it contains a unit, which means it's the whole thing. This is actually the idea.
You said, do we already,
Have we proven that yet? We have not.
do we already know that like the trivial ideal is maximal?
The trivial ideal is maximal. The trivial ideal is very much not maximal because it is properly contained in this guy, which is not equal to the whole ring. I'll give you a hint. One thing we're eventually going to prove is that if you take any polynomial ring over a field, it's going to be a PID. So polynomials over the reals, polynomials over the rationals, polynomials over the complex numbers, those are all PIDs. And we haven't proven that yet, but we will. So, integers aren't a field, so how about integer polynomials?
Here we get what he was mentioning, 2 comma x does not generate the whole thing.
Yeah, here 2 is not a unit in the integers, so 2 is not going to give you every other element. In fact, this is the set of all polynomials g of x in the integer polynomials, such that g of x is equal to 2 f of x plus x times h of x for some f of x and h of x coming from your ring.
Which is to say, constant terms have to be multiples of 2.
Yeah, which is the same as saying it's a set of all f of x integer polynomials such that f of 0 is even. That's going to give you an ideal that is not principal. No matter how much you try and generate this thing by a single element, there's no way to do it. And since that ideal is not principal, this is going to not be a PID. Any questions or comments about that? Yeah, Ellen?
What about ZI?
Woo! Z joined I. That's a fun one. That's a lot of fun. So much fun to work over that you'll have 45 minutes of enjoying it in homework 2. Well, technically in homework 2, I'm having you prove that Z adjoined I, so the Gaussian integers form a Euclidean domain, and as we're about to prove, every Euclidean domain is a PID. So in homework 2, you're going to indirectly show Z adjoined I is a PID. Quite. Speaking of which, let's take a look at that. Oh, before I forget, but Dr. Gerstle, what about 2 comma x over here? That's not a principal ideal. It's true that 2 comma x here doesn't look like a principal ideal, but turns out that x isn't giving you anything that 2 doesn't already give you. So the fact that you can find a single element that also generates the exact same ideal as 2 and x here means that this is principal. It just doesn't look like it at first glance. Whereas here, no matter how hard you try, there is no single integer polynomial that will generate the exact same ideal as 2 and x. So let's take a look at this next thing. Next theorem. Next theorem is going to be every Euclidean domain is a PID. But Dr. Gerstle, does that mean every PID has to be a Euclidean domain? It does not. Jonah, can you think of a counterexample to for a PID that's not a Euclidean domain? Did I would be extremely impressed. Here's one. Here's an example of a PID that is not a Euclidean domain. Let's take Z adjoin something, except instead of adjoining I, we're going to take 1 plus square root of negative 19 all over 2.
Excuse me?
Oh,
What?
goofy.
Why would you do that?
You should have it written down.
Which, as a set, is equal to the set of all elements of the form A plus B times 1 plus square root of negative 19 over 2, where A and B are both integers.
Yeah,
Sure. No.
Does it have to be that ugly?
I mean, what if we
As it turns out, yeah, it kind of does.
really?
There are no simple examples of this.
Why is it negative 19?
Why not?
What if you did like negative 3?
Wouldn't work.
Really?
Really?
What about 7?
That would be not a PID, I'm pretty sure.
Why does 19 work?
Why does 19 work? Who knows? Well, so I'm not going to prove this right now because this is actually as you might guess, a bear to actually try and prove anything with.
This is going to be on the wall.
But I would not put that on the homework. No, I'm giving you Z joined I on the homework, and that's complicated enough.
It'll be in class exam.
Don't give me any ideas. Don't give me any ideas, or I'll put it on the final.
Let's give more ideas.
There really, I'm not joking around when I say there is not a more clean example of this out there.
That is crazy.
At least, I mean, there's other examples of PIDs that are not Euclidean domains, but none of the ones I've ever seen before are any nicer than this one.
That's scary.
Z adjoined E,
What?
that I'm pretty sure is not PID.
Also, why is it square root of negative 19 and not just I root 19?
And you could
Okay.
do that. I mean, that's the same thing. If you want to do that, then fine.
I was curious if there was a difference, but
No.
it would not make
I
sense.
hope not.
Better not be.
It better not be.
Once again,
Everything you
I'm
could not
still
be
learning
sure
about
about.
Let's prove the theorem. Turns out proving this theorem is a lot easier than proving this example.
Wow.
Let me get some decent ways into this. So we need to start off by taking a Euclidean domain and showing that it necessarily has to be a p-value.
We do have 25.
Mimi? Is that you, Mimi?
God, now.
Tom, that was your
Oh,
computer.
gone
And
now.
then go into the cloud.
She just walked by with Dr. Kumar.
They left the hallway. Alright, let's prove this. So what do we need to do? We need to start by assuming we have a Euclidean domain. We need to take an ideal, and we need to show that that ideal can necessarily be generated by a single element. So we're going to let R be an Euclidean domain, a Euclidean and an ED, say. And we're going to let S be an ideal in R. And what we want to show is that S can be generated by a single element. Sound good? All right, so first thing we need to immediately do is just consider the trivial case, where S is trivial, because it turns out that's not going to work for what we do for the remainder of our proof. So right off the bat, I'm going to say if S is the set containing 0 and nothing else, well, anybody want to take a stab as to what element of our ring is going to generate the set containing 0 and nothing else? Jackson, you want to give it a guess?
0.
It would be indeed the ideal generated by 0. All multiples of 0 are going to give you, well, 0. And that's it.
That's the most devastating result of this class.
It's not been a result of this class, it's a result of last class. So we're going to assume that S is not just, that S contains a non-zero element in it. So now, what we're going to do is we're going to do something sneaky. We're going to pick B to be the element in S such that for all little s coming from the ideal, delta of B is less than or equal to delta of S. Why do we know we can do this? Well, if you take, even if S is an infinite ideal, delta of S, the image of S, when we plug everything in S into delta, is just going to give us some set of non-negative integers, right? If you have any set of non-negative integers, no matter how big it is, it's going to have a minimal element. Why? Because integers are a discrete set that are bounded below. They're a totally ordered set that's bounded below. So they have to have a greatest lower bound that lies within the set. Boom, I threw some real analysis at you.
Can we not do strictly less than?
We can't do strictly less than because delta of B cannot be strictly less than itself.
Oh, right.
And we can't even exclude that case because there might be multiple elements in the set that happen to have the same that happen to have the same delta value. In fact, I can assure you that will always be the case for a non-trivial ring and a non-trivial ideal. Because reasons.
So B is the element that gives us the least delta we can get.
Exactly. out of everything in the ideal at least. There's potentially elements outside the ideal that have smaller delta values, but B is the smallest one in S that gets this job done.
Wait, sorry, why did you say that we knew there was a new one?
It's because delta maps to the non-negative integers, and if you're taking any set of non-negative integers, it's always going to have the smallest element, even if it's an infinite set. It doesn't necessarily have to have a biggest element, but it is going to have a smallest element.
I forgot that it mapped to integers.
It's important here that delta is mapping not only to A, the integers, but also to B, the non-negative ones, to guarantee there's a smallest one. That makes sense? Here's my claim. I claim that that element B is necessarily going to generate the whole ideal. Yeah, that's convenient. So let's see if we can prove that. So, what's this? How are we going to prove that? With some good old-fashioned Euclidean algorithming. So we can say that given any element A and S, well, since B is non-zero, I should make a note. We want B to explicitly be non-zero, or this argument falls apart. Which we know we can do because we're assuming our ideal is non-trivial. So given any element A in our ideal, well, we have an element A in S. We have an element B not equal to 0 in S. Let's use the Euclidean algorithm, guaranteed by the fact that we're working over a Euclidean domain. There must exist Q and R coming from our ring with A equals QB plus R, where delta of R is less than delta of B. So again, just kind of applying our condition for just applying our Euclidean algorithm, what does that guarantee? Well, what do we know then about, I want to take this equation right here and flip it around. I'm going to write R is being equal to A minus Q times B.
We know that subtraction still works on
Subtraction works in any ring.
Right. Okay.
It comes from the fact that any ring is necessarily an abelian group under addition, and any group has to have additive inverses and subtraction. So what do we know about A? We know A has to lie in S. What do we know about Q times B?
Doesn't that also have to lie in us?
Well, we know B has to lie in S. Q doesn't have to lie in S necessarily. Q could be anything in the ring.
But doesn't Q times B have to lie in us?
But part of being an ideal is that anything in the ideal times anything in the ring whatsoever has to lie in the ideal. So you're right, QB does have to lie in S. I will note that Q itself doesn't have to be in S, but QB does. So R has to be an element in S. But what's the problem here? Delta of R has to be strictly smaller than delta of B. And B was the smallest non-zero, had the smallest non-zero delta value. But so we can in other words say, since delta of B is less than or equal to delta of S for all S not equal to 0 in our ideal, R has to be 0. And that's taking up too much space on its own. Questions or comments? Sort of like the ones we did back in Math 410 when we were doing cyclic groups. In order to prove something about a cyclic group, we do Euclidean algorithm, show the remainder term has to be 0 by minimality of the remainder. Turns out, turns out the same sort of argument here can tell us that our remainder has to be 0 in whatever arbitrary Euclidean domain we happen to be working over. Questions, comments? So what does that tell us? Well, then it tells us A has to be equal to Q times B. Hence, A is a multiple of B. So in other words, A is in the ideal generated by B. Because the ideal generated by B, by definition, is a set of all multiples of B in the ring. Well, since A was arbitrary, we've shown that every element in the ideal is contained in here. So that tells us that S, by definition, must be a set of all multiples of B. Let's say RB. And now let's say SB, S coming from S. SB equal to the ideal generated by B. Thus, S is principal. And since we've shown that any arbitrary ideal in our ring has to be principal, either by this 1.2 line argument or this argument, we can conclude R has to be at the ideal. As the prophecy has foretold. Here's a quick corollary to round things out. Integer polynomials. Not a Euclidean domain. Why? Because integer polynomials, we know, are not a PID, and since all Euclidean domains are PIDs, something that is not a PID cannot possibly be a Euclidean domain. And I think we will leave things off there for today. Alrighty, hope you all have a good one. Went a little bit fast there towards the end, just in interest of wanting to finish this proof on time. When we come back on Thursday, we have another 12 minutes, don't we?
Yeah.
I hate this class. Okay.
We have a lot more.
Why am I so convinced that it ends at noon? Thank you, Eliros. Okay. Sure. What is the day you're dropping my class? Okay. In the future, please don't come into someone's class and do this, but okay.
I thought class was ended, Dr. Gerson. You probably heard that and just came in.
Lincoln smack it.
That's
Okay, well, since we have 15 extra minutes, or 13, 12, however many extra minutes, anybody have any questions about this proof? Yeah, Matthew.
Okay, this might just be bad, but like, what's an integral domain?
Good question. Integral domain. Yeah, we talked about this last time, but I don't think it's been in a formal packet yet. I really should put it in one. So, integral domain is just a ring that has three things. One, multiplication is commutative. A times B always equals B times A. Matrix rings need not apply. Two, you have to have multiplicative identity. And the big one, no zero divisors. Which is the same as saying if A times B is equal to 0, then either A equals 0 or B equals 0. So, in other words, in an integral domain, there's no way to multiply two non-zero things and somehow end up with 0. Whereas, contrast that with like a matrix ring, where if you were to take, for instance, 1, 0, 0, 0, a non-zero matrix, multiply it by 0, 0, 0, 1, another non-zero matrix, you would get the zero matrix, even though these were not zero matrix to start with.
So like Z mod n and stuff,
would end up being, like, you wouldn't work for this because you could have two things multiply together to get 0.
It works if and only if it is prime.
Probably makes sense.
Like in Z mod 60, for instance, you could take 2 times 3 and get 6, which is the same as 0. But if n is prime, Z mod PZ does turn out to be an integral domain. Because due to the lack of factors. What's everybody grinning at? What's happening? I'm scared. Okay, I'm gonna pretend this is going on. So this gives us a hierarchy. We have fields, which are all Euclidean domains, which are all PIDs, which are all I don't know, something, which are all integral domains. Today we proved this implies that and that implies that.
Is that what we're gonna keep on doing?
On Thursday, we get approved. The
This-
missing link. The
Oh.
missing link.
I can guarantee we're not going to finish proving both of these arrows on Thursday.
But will we at least figure out what the other one
Oh, okay, this arrow is going to be by definition.
Oh.
What this one is? I'll give you a hint. It's a UFD.
So,
Unidentified
domain?
flying domain.
That's the same joke Dr. Gabler made to me this morning. Yeah, we're going to talk about unidentified flying domains. Unidentified flying domes, that's right. It's just a standard flying saucer.
There you go.
Is it
And-
uniform?
Wait, but then it would be
It is not.
identified.
Oh,
It is another U word. Hi, man.
Unitary.
It's not unitary.
Oh, we're.
Ugly.
I'll give you 3 more guesses before I make you wait.
Universal.
It is not universal.
Unsolved.
That's actually more relevant than you'll think in this class, but no, it's not that.
Oh, shoot.
Unity?
It is not unity or anything relating to, well, I guess it is related to 1 in some way.
Oh,
It's unique.
what's that?
Factorization.
Yeah, you need
What's the D?
factorization
Domain.
You do, oh, okay. Well, we got one part of it
Wait,
right.
you talked to me about this enough, because that was so
I probably did.
funny. Yeah, because I
I'll give you a hint. UFD, and that's going to be in the next packet. We're not done with this one yet, and we're not going to finish it today. But UFD is basically going to be a domain where every non-unit multiplies into a product of
Pseudo primes.
unique primes.
Yeah.
Unique primes. I'm going to put both of those in quotes because both of those are actually irreducibles, actually.
There are no-
What do you mean when you say unit?
Unit, I mean something with a multiplicative inverse.
No, they're just not real.
That's right.
Does it have like an element, but with
Real
like
primes?
a
Something that you can
All of it.
A is a unit if there's something in your ring you can multiply A by in order to get to 1.
It's redundant. Every real is prime.
all kinds of real.
Alright, John.
Also that.
Well, all friends are
That's
real.
what I
All reals are prime.
Therefore, so that doesn't make any sense. It doesn't.
Let's see, do I want to talk about GCDs?
No, I think they were all not friends. Yeah.
Divisors. They're all prime.
Yeah, you know what? I'll introduce them. Turns out,
Definition of-
Your work.
shut up, class is still going. Turns out, as long as you're working over a Euclidean domain, you can take the GCD of any 2 elements. You might have to get a bit creative with how you find it, but you can have greatest common divisors in a sense.
Do we have to take it through the delta function?
Do we have to what?
Do we have to shunt it through the delta function?
Oh no, do we have to use the delta function? Actually, no we don't, because it actually works over a PID. You don't even need it Euclidean.
Really? Oh.
Having the delta function makes it a lot easier to actually compute.
I was wondering if you read the tells that we actually use a different letter.
So here's the thing about delta. The textbook we're using uses delta, which is why I'm using delta. I've never used delta to refer to this norm before in my life. I'm used to it being the letter N. So if you ever see me write a capital N instead of delta by accident, it's because our textbook has weird notation in that regard.
Capital N. Like the
'Cause it-
natural numbers.
More like the word norm, but
Yes.
norm.
Oh, and that's
like analysis norm.
That makes sense.
Lincoln can tell you a thing or two about those. So I'm going to introduce to you a theorem, and then the definition is going to kind of come as a result of the theorem. So these common divisors. If R is a PID, and A and B being not equal to, actually no, both of these being non-zero elements in R, then there exists some element D in your ring such that the following two properties hold. D divides A and D divides B. For this one, what does it mean, Dr. Gerstle, for D to divide A? Well, that just means A equals XD for some X in our ring. In other words, A is a multiple of D. Say what?
LOL XD.
Oh, well, yes. And secondly, not only does D necessarily divide A and B, but also, if some other D prime happens to divide both A and B, then D prime also has to divide D. And here's where the greatest part of common divisor comes from. The fact that if D prime is any other common divisor of both A and B, then D prime has to also be a divisor of the GCD. And if this and in this case, we're going to call D greatest common divisor, or GCD. Of A and B. So that's what a GCD is in general. This is as long as you're working over a PID, it's an element D in your ring that satisfies these properties. And the theorem says all non-zero elements are guaranteed to have a GCD. Here's a word I want to emphasize that I wrote on the board. By which I mean the GCD is not necessarily unique.
No.
You can have many different GCDs.
No, oh shoot.
And a PID. Don't worry, they're all strongly related to each other.
Wait, so does that mean we can have like a set that's like D bar, but it's just all the GCDs?
Sure.
Oh yeah.
It's not a very, well, I'll tell you what that set is next time.
What?
Let's cut it there for today. So next time we'll talk about how do you actually, we'll prove this theorem, prove that GCDs exist, talk about how do you actually compute these things in an arbitrary Euclidean domain, and especially, or in a PID, but especially in a Euclidean domain, where actually the computation is, there's a nice way to compute. Hint, you do what you did in number theory if you found GCDs then.
Yeah.
And after that, we probably in the second half of class Thursday start talking about UFDs. Hope y'all have a good one. See y'all Thursday.
A greatest common divisor.
Hey, greatest commonizer. Oh, end the video. Bye, Libby.